Welcome to Saxon Math Course 3, Lesson 117, which is about significant digits. Now, significant digits represent a concept related to measurements. Now, when you measure something, you usually use a tool to do the measuring itself, a ruler or a scale if you're doing weight, and a ruler or scale, they have a certain amount of precision. Now, significant digits represent the accuracy of a measurement. Now, when we have a measurement, a ruler such as the one I use in our videos, which I have over here, is pretty precise. If we look at it, this ruler goes down to millimeters. On this side, it's got inches, pretty large, but then it has half, quarter, and 1/16 of an inch. So this ruler here, these measurements with the 1/16 are a little bit more precise than these measurements on the inside, which I think only go down to the eighths. So this side gives you a closer measurement than this side does. This one is more precise, and this one is less precise. Now, those two rulers are still pretty close, but you can imagine if I had a ruler that just had the inch marks, I could only say that it was close to 1 inch or 2 inch or 3 inches. As I get more and more precise, I could have tenths, hundredths, and thousandths on a ruler. Although at that point you'd probably be using a tool called calipers, which are used to measure small distances and thicknesses. Now, in order to find the significant digits that represent the accuracy of the measurement, we use 6 basic rules. The first rule, very straightforward. You count every non-zero digit. So any number that's not a zero that's in your measurement counts as a significant figure. Then you have to count all of the zeros that are between two non-zero digits. So, for example, if you had 101, we have 2 non-zero digits and 1 zero between them, so that would be 3. Now, if you have a decimal, such as 101.0, you count the trailing decimals on the right-hand side. However, that would make this 4. If I put a 0 in front, it doesn't actually change my significant digits, because this doesn't represent the accuracy. You can picture this as the more zeros I add down to the right, the more fine the space between the lines is, the more precise your measurement is. Now, you're going to count all of the trailing decimals on the 0. You're not going to count zeros to the left of the decimal unless they're in between 2 digits. And if you have a whole number that doesn't have a decimal place, then trailing zeros to the right are ambiguous. What that means is this could be 2, 3, or 4, because we're not sure quite how this is measured. If I was using a stick that was 10 feet long and found I needed to use 120 of them about to go my distance, then I wouldn't really have this last digit as part of my measurement, because I didn't measure that it was 120,000. I measured it was 120 10-foot segments. Now, exact numbers have an unlimited number of significant figures, and that sounds a little bit weird, because you'd think something like the conversion rate for feet to yards being 3 feet per 1 yard would have one significant digit, because there's only one digit. But you have to remember that we're talking about the preciseness with which something was measured, and there are exactly 3 feet in 1 yard, meaning you could have an unlimited number of 3.00000 and zeros going on forever to the right. So if we have exact conversions, those conversions are going to have unlimited significant digits. And this becomes important as we move into how we use significant digits, because it's very easy to count the significant digits, but it's a little bit harder to know how to use them when you have two different measurements with two different amounts of significant digits. Now, in example 1, we're going to be just stating the significant digits. If we have 2.5, it has two non-zero digits. It has two significant digits. 30.5 has 3, 1, 2, 3. And 9.3 times 10 to the power of 7, well, scientific notation is actually perfect for significant digits, because in scientific notation, we only look at the left. So we have 9.3, so that's two significant digits. Well, what about a mile is 5,280 feet? Well, that's a conversion ratio. And since we know that a mile is always 5,280 feet, this has unlimited significant digits. Because that's not something you measure. You don't measure that with a ruler or a yardstick. You just know it, because that's the way it's defined. Now, there are rules for multiplication and division with significant digits. If you multiply or divide two numbers that have significant digits, two measurements, your answer can only have as many significant digits as whichever one was the one with the least significant digits. So if you have two products, one product has 4 significant digits and the other one has 2, then your answer has to have 2, because 2 is smaller than 4. For addition and subtraction, it's a little bit simpler. You use the smallest number of digits to the right of the decimal as the decimal places in your answer. So, for example 2, we're going to have a division problem. We have 8.9 divided by 4 equal parts. Now, 8.9 divided by 4. If we divide 8.9 by 4, we can think about 4 will go into 8 two times, 9 two times, with one piece left over, which would be 10, which would go 2, 5. So we'd have 2.225. Now, 2.225, we have our ratio here, which has an unlimited number of significant figures, because it's just what we're dividing it into, how we're splitting it up. And then we have our measurement. It was 8.9. This only has 2 significant figures. So that means this number only gets to have 2 significant figures. And that's how that works. What about the volume of a cube with edges 1.2 millimeters long? Well, volume is the edge cubed. So 1.2 times 1.2 times 1.2, that would give you 1.728 millimeters cubed. But again, there are only 2 significant figures. So that means it would be 1.7 millimeters cubed. Now, with addition or subtraction, if we imagined that a test tube contained 6.24 milliliters of liquid before it was heated and 4.6 milliliters after it was heated, and we were asked how much of the liquid evaporated, well, we would subtract 6.24, we'd subtract from that 4.6. Now, I'm going to have to borrow. 12 minus 6 is 6, 5 minus 4 is 4, and this 4 is just going to drop down. But notice the smallest decimal place is right here. That means I can only have this answer here of 1.6 milliliters. We can't include that 4 because the second measurement didn't have a digit in this hundredths place. If it had had a 0 in the hundredth place, then it would be 1.64. But we have to keep the integrity of our measurement. And the reasoning for this is we don't know that it was 4. 4.6 ends here. If it had been written as 4.60, then we would know that it was in fact exactly 4.6. But since it was left as just 4.6 and not 4.60, then we don't know if the graduated cylinder in which it was measured could measure to that exactness, which means it could have been 4.62 or 4.63 or 4.64 even, if it just rounded to the nearest one of 4.6. So we can't say what number would be there, so we don't put a number there at all, and we just leave it as the simplest number of decimals, which would be 1.6. Now, that has been lesson 117. I hope you all stay safe, stay inside, and wash your hands.